Okay, welcome to the ninth lesson about thermodynamics, which is a rather special topic because thermodynamics deals with macroscopic bodies, macroscopic systems composed by many parts, essentially an infinite number of parts. And what is important is that thermodynamics is extremely general. It means that it does not assume almost anything about the microscopic composition of bodies. And so, as Stein said, the conclusions by thermodynamics are extremely general. But on the other hand, it needs some phenomenological law. For instance, how system behaves, so essentially the equation of state of the system. And another point is that thermodynamics, classical thermodynamics at least, deals with the system at equilibrium. So time has nothing to do, almost nothing to do with thermodynamics. So we have to consider a system that had enough time to relax to the asymptotic state or to equilibrium. Okay, so thermodynamics of a system is described using a set of coordinates called thermodynamic coordinates. For instance, for a fluid gas, for instance, we can think of a piston, of a cylinder, of a surface S, and the piston includes a volume of height h, so the volume is S times H, and we can assume that the piston exerts a force on this gas, for instance, M times G, or a force F. Clearly, the pressure P is the force divided by the surface. And we can also introduce the density, for instance, of the gas, dividing the mass of the gas, not the mass m, by the volume and so on. And the work is the force times the displacement, so for F times dH, but since F can be written as P times S and H as V over S, essentially the work done on this gas or by the gas is a PdV. And but we can also use another system, for instance, a rubber band. And in this case, the coordinate is the length, the tension, for instance, the mass, the density, and so on. And in this case, for instance, the work is the tension times the increase of length. Well, the pressure can be measured using, for instance, a manometer, which is a new shape pipe, generally of glass, closed, so that here there is vacuum, and so the difference in the pressure here, so the pressure here is given by the weight of this column, so essentially divided by the surface. So using a high density liquid like mercury, which is 13 times denser than water, one can have a manometer that has a small size, small in the sense more or less 1 meter, because for instance, the pressure, atmospheric pressure, normal atmospheric pressure is 76 centimeter of mercury. So essentially, you need something of the dimension of 1 meter. Clearly, now we use other system, electronic systems, so we can have manometers which are extremely compact. Temperature is a physical quantity that is related to something more or less mysterious. So let us start by the sensation of temperature that you can have with your hand. If you touch something which is hot or something which is cold, you have a different feeling. But it is also known that, for instance, if you put your hand before in a container with cold water and the other, for instance, in a container with hot water, when you touch the same object, you feel different temperatures because your sensors are not very accurate. So we need something objective, and we can use any system essentially which changes some of the coordinates with the temperature. I mean, if I put this system in a vase containing cold water, something changes. For instance, the rubber band becomes smaller or larger, larger in this case, while the gas becomes smaller, and the opposite in a vase containing hot water. And so if you put this data on a sheet of paper, you can, for instance, by calibrating the water by mixing a certain quantity of hot water at the same temperature with a certain quantity of cold water, you can have a plot that relates an abstract temperature with some physical property. Normally, thermometers are calibrated using 0 degrees Celsius ice in equilibrium with water at standard pressure, and boiling point of water, which is water in equilibrium with vapor, again at the standard pressure. And so you have 2 points, and using these 2 points you can put all thermometers in rough agreement. Rough because it is not said that the scale temperature of a thermometer is linear. In general, it is not. So you can have nonlinear relationships. This means that even though you have calibrated the thermometer at certain temperature, in the middle you don't have the same reading. Clearly, you can detect linearity of a thermometer because if you put, for instance, by mixing water, you can have intermediate temperature, and you see that it is not linear, or by expanding the relationship linearly, you see if it deviates. So, but luckily, we have at our disposal linear thermometers, which are thermometers made with a perfect gas, which means or an ideal gas, which is a gas at low density, a very rarefied gas. If you plot these curves for different gases, you see that you can have different volumes for different temperatures, but the relationship is linear. But if you extrapolate, you see that all these curves would tend to have a volume 0 at a certain special temperature, which is the absolute 0, minus 273 degrees. And by putting the 0 of temperature scale here, you have a real linear relationship without any constant. So essentially, this is one of the first reasons for choosing this as the origin of our temperature scale, so that we can have the perfect or the ideal gas law, PV equal to nRT, where n is the number of moles of the system, which is a mole is an Avogadro number of molecules, so 10 to the 23 molecules, and R is just a constant for changing the scale, because from one side we measure the temperature in degrees, and the other side we have something which has the dimension of the work, so a joule, and so we need a constant for converting these two. And clearly, no real gas is still gas, or neither an ideal gas at this temperature. All of them can change state, it becomes liquid and then solid before arriving at this temperature. In the graphs in thermodynamics are mostly done using the Clapeyron plane, the plane where the coordinates are PV. And in these planes, we can have essentially, we can draw curves. Now, if you draw a curve on this plane, means that every point of the curve have a definite volume and pressure, so density and pressure, say. This means that the system has to be always homogeneous. So, for instance, if you, say, put a gas into a rubber ball and then you make it explode and the gas expands into a container, actually different portions of space have different pressures and different densities. So in principle, you cannot draw it as a line on this plane or any other thermodynamic plane because it is not homogeneous. So essentially, whenever you plot a curve here, you mean that you are making a very slow transformation, a quasi-static transformation, so that the system is always near equilibrium. So for instance, these are, say, constant temperature curves of an ideal gases, which are hyperboles, while these are isocores, so it means transformation at a constant volume. Clearly, we can have also transformation at constant pressure and so on. This plane is particularly useful because if you draw a cycle, for instance, obtained also experimentally from a machine, actually this is the watt indicator, because watt used to connect the piston of the steam machine to the sheet of paper, so that the sheet of paper oscillated with the piston. Then the manometer to the pen, and so he had the two things that moved and formed a cycle on this sheet of paper. Now you can see that the area inside this cycle oriented, that means that it is positive in one orientation and negative in the other. It is the work done by or on the system. So this was particularly useful at watt times, because in this way Watt could tune the pieces of his steam engine in order to increase the area of the plot, so to increase the work done for a constant amount of coal. Okay, the ideal gas is not very accurate except for extremely rarefied gas here. You see, for large volumes, large pressure, and sorry, not so large pressure, say. While, for instance, a more accurate equation that describes also the phase transition from gas to liquid is the van der Waals equation, or others. There are several different ways. For instance, another one which is particularly convenient when dealing with the statistical mechanics is the virial expansion, which is a series expansion in terms of 1 over v. But clearly there are more others that are more accurate in different parts of the diagram. This is just for say that there is not only the ideal gas law. Okay, we have spoken about temperature, but another concept that is related to thermodynamics is heat. Now, heat and temperature sometimes are confounded, but they are not the same. Heat is just energy, but for mainly historical reasons, you cannot speak of the heat contained into a body, because this resembled too much the idea of considering heat as a fluid, but which is not right, clearly. So we speak of heat when we exchange energy between, say, bodies in energy, which is in thermal sense, so essentially something which has a certain temperature. And we can start defining heat in a practical way, so defining the calorie, which is the amount of energy that rise, say, a kilogram of water from a certain temperature to another one. Actually, this is called the large calorie, because the small calorie is that needed for rising a gram of water. So one is 1,000 the other. And Joule performed an experiment simply dissipating the potential energy of a body, which could be measured accurately using standard methods, into heat simply by friction. And in this way, it was able to compute the equivalent in joule of a calorie. So a large calorie, is 4,000 joules, essentially. And another thing that we can define is the heat capacity. The name resembles the idea that at that time heat was considered the fluid, so the capacity is just as the capacity of a vessel, and so the quantity of heat is the capacity times the variation of temperature, which is essentially the equivalent of saying that if this is the volume of a fluid, this is the width of the container, this is the height of the fluid inside the container. Clearly, this is not true, but the idea is this one. We can also define a specific heat, which is the capacity for unit, say, of mass or unit of number of particles, mole. And one of the goals of statistical mechanics is to derive how, for instance, this specific heat behave, or its number, its value, according with a certain model, microscopic model of matter, and we shall see about considering the law of quantum mechanics. Okay, so let's pass to the principles of thermodynamics, in particular to the first principle, which is nothing but the conservation of energy. So essentially says that the quantity of thermal heat, the thermal energy that can pass to a system is either converted into internal energy or in the work done by the system, or according to the sign. So heat is considered positive when it is entering into the system, and W is considered positive when it is exiting from the system, because clearly this was what interested to engineers when dealing with the steam engine. How much coal I have to put in to get a certain amount of water pumped from a mine or something like this. The internal energy is essentially the energy which is stored inside, for instance, a gas. It is stored as a kinetic energy of molecules, potential energy, for instance, if I have molecules that can oscillate, they can have both kinetic oscillation, kinetic energy related to oscillation, and also potential energy, for instance, in the spring of the oscillation. If they can rotate, I have also kinetic energy related to rotation. So all of this is called internal energy. And the important point is that the internal energy is a state function, because since we assume that the gas has enough time to reach equilibrium, it does not depend on how so this energy was communicated, because at the end it redistributes to all modes of the gas. So due to the fact that we expect long enough, the internal energy is a state function, so it depends on the coordinates and not on the history of the system. And so, for instance, in the total variation of this internal energy in a cycle is zero, because the system comes back to the initial state. While, for instance, clearly the heat and the work are not state variable, because it depends, for instance, by the fact that the system has turned in a cycle or not, and so they cannot be state functions. And so, since the variation of heat can be expressed in terms of the heat capacity, I can replace it into the first principle, and for instance, working at constant volume, since the work done is PDV, so it is zero, we have that the internal energy, delta U, is exactly equal to the variation of internal energy, is equal to the specific heat at constant volume times the increase of temperature. While if I make a transformation at constant pressure, I have also the work done here. And so now putting here the state equation of an ideal gas, so this is only valid for linear gas, I see that the delta U can be also written as the specific heat at constant pressure minus nR, and so times delta T. And so essentially I have that the constant, the heat capacity at constant pressure minus the heat capacity at constant volume for an ideal gas is equal to nR. And since I can convert the uppercase C to lowercase using the specific heat, molar specific heat for unit of number of molecules, I have this Mayer relation that is Cp minus Cv equal to R, which is valid only for ideal gases. And another consequences that comes from statistical mechanics is that the specific heat of a dynamic gas is 5 over 2, and clearly from here one can compute the specific heat at constant pressure, which is 7 over 2, and other quantities that may be interesting is that the specific heat, in this case mass, for unit of mass of water, is essentially the definition of calories, so it is 4,000, etc., etc. Of ice is less than this, and of iron is about even less. So this means that iron becomes hot when I communicate a small amount of, sorry, a given amount of heat, while water is still cold. Okay. Another kind of interesting transformation is the adiabatic transformation, where there is no exchange of heat. In general, a rapid transformation, here clearly we have to use several approximations, because we have seen that rapid transformation in general are not in equilibrium, so they cannot be really represented in the Clapeyron plane. But if the system is small enough, you can assume that it is not very far from being homogeneous. And since it is extremely rapid, for instance, explosions or wave compressions, for instance, for computing the speed of sound in air, for instance, one has to use an adiabatic transformation, because in the time that the wave passes, the system has no time to exchange heat with the surrounding. And for an ideal gas, we can compute the shape of an adiabatic transformation from the first principle by putting delta Q equal to 0, and so delta U is NCV delta T, and so for the work I use a PDV, and so I get, by putting this with some algebra and computation of an integral, I get the equation PV to the power gamma equal to constant, where gamma is the ratio between the specific heat at constant pressure, and the specific heat at constant volume, which is 7/5 for a diatomic gas like, say, oxygen, nitrogen, and so on. And the important point is that you see that since for an isotherm you have PV equal constant, here you have PV to the power gamma equal to constant, and gamma is not so different from 1, the two curves are very similar. Okay, now we have spoken about transformations, but you have to be careful when considering a reversible and irreversible transformation. So reversible means that I can transform heat in work and work in heat in a reversible way. This cannot be done, for instance, if the transformation implies the contact between two bodies with a finite difference of temperature. This is the essence of the second principle of thermodynamics, or when it implies the dissipation of work into heat, like in the Joule experiment. So, but there are these two different kind of transformation, and the essence of the second principle of thermodynamics is to define a quantity which is different in these two different kind of transformation. But before arriving at the second principle, we have to introduce a thermal engine, which is essentially why thermodynamics was laid down by engineers. So a thermal engine is an engine is by definition something that performs a cycle, so that after a cycle returns to the same state. And thermal means that it is the origin of movement is the difference of temperature between two thermal reservoir, two sources of heat. So the idea is to extract heat from one source and discharge other heat to another source. In the mean, it performs a cycle, this is represented by this circle, and produces work. Now, from the first principle, work, since the variation of internal energy of this engine is zero, work is just the difference of Q1 and Q2. Actually, this is the sum because of the convention of signs. And we can define the efficiency of a thermal engine as the ratio between the work done and the heat absorbed. So essentially, as I said, a quantity of water pumped from a mine divided by the quantity of coal that I have to put into the engine. Now, using the first principle, this W is this one. I put into evidence the minus, but I had to put an absolute value here because this quantity for the convention of sign of thermodynamics is negative. And so it comes out to be this one, or this one if you use the algebraic definition of work. So essentially, this one is negative and the other is positive. Okay, so the second principle says that it is not, there are two way of stating the same principle. Clausius' formulation is that the heat can never pass from a low temperature reservoir to a high temperature reservoir without using clearly, for instance, a refrigerator, so without paying the bill. So it cannot, I cannot construct a device that makes this transformation without changing something in the environment, without absorbing work. And Kelvin says that essentially we cannot extract work from a single heat reservoir, a single heat source. So I always have to discharge part of the energy into another reservoir, and I shall show that this has a profound analogy with the water wheels. The two statements are equivalent because I can construct, by violating one, so supposing that I can construct, for instance, an engine that can, extract heat from a low temperature reservoir and communicate it to a higher temperature, then I can reuse the same quantity to produce work. And if I calibrate so that I actually are not discharging or removing anything from the low temperature reservoir, I have a violation of the Kelvin statement, and the reverse for the Clausius statement. Okay, actually, what is important to understand is that these laws are in profound conflict with our naive idea of how a mechanical world works, because in principle it is not impossible to devise engines that violates the Clausius or the Kelvin statement. For instance, in this case, it is the Maxwell demon. Maxwell demon is a being, a teeny being, that can maneuverate a door separating two gases. At the beginning, they are both at the same temperature, but the same temperature means that there are some molecules which travel slower and some others which are faster. Then, if he can see when a faster molecule approaches this door, or when a low velocity one approaches from the other side, it opens the door, and otherwise it keeps it closed. Since we assume that the door has a very vanishing weight, now what happens is that this demon can actually separate a faster molecule from a slower ones without doing any work, so violating essentially the Clausius statement. Another hypothetical, classical, so mechanical device is this Feynman-Miluchowski ratchet. Essentially, it is a kind of wheel inside the gas that is so this has to be more or less of the same mass as the molecules in the gas, so molecules can hit this mill from different sides, and so sometimes they try and tend to make it turn in one direction, sometimes in the other direction. But actually, here I have a pole, so this is a ratchet, that can only turn in one direction. So only when molecules from the right direction hit, it makes a small turn and can rise, say, a small amount of mass. Or, for instance, if we think to molecular machine, a molecular machine could use this source of energy to move inside, say, a body or inside a cellule. And so, in principle, this would violate the Kelvin statement of the second law. And so, why are not they are not working? There are several reasons, several explanations. The one, for instance, is that in this case, this demon has to see, for instance, the molecules. In order to see molecules, it has to, say, receive photons from these molecules. But actually, in order to receive these photons and to see them, it has to be at a temperature lower than that of the molecules. Otherwise, it cannot. So the optical device of this demon cannot distinguish between photon emitted by the demon itself or photon emitted by the molecules. So essentially, the demon in this case is the heat, the low temperature heat reservoir. Or another explanation is that this door, which has to be of the same mass of the molecules, has to be not to fluctuate. But in order not to fluctuate, so not to open by itself, it has to be at a lower temperature with respect to the molecules, and so essentially these are the main reasons. The same reasons apply here. In order for this system to work, this pole has to have a mass comparable to that of the molecules, otherwise they could never make it turn. But if it has the same amount of heat of mass of the molecules and at the same temperature, then it fluctuates, and sometimes it rises by itself. So in order not to do that, this has to be kept as at lower temperature, and again this is the low temperature heat source that makes this system work in spite of the second law. Okay, so assuming that the second law works, now we can build an hypothetical engine, the Carnot engine, that works with only two heat sources, one at high temperature and one at low temperature, by using two isotherm and two isoentropic or adiabatic transformation, as divided here. Remember that this figure is greatly exaggerated. In order to have a sensible work done by a Carnot engine, I would need, since this is very straight, I would need an extremely large variation of volume. So I would need a very large cylinders, very heavy pistons, and this is the reason because we never use a real Carnot engine in spite of its high efficiency, theoretical efficiency, to perform real work. And if you compute the variation of work and heat on this transformation, you discover that the actual efficiency of the Carnot engine is given by simply the temperature, the ratio of the temperatures of the two heat sources. And we can also show that since this is a reversible engine, it can also act as a refrigerator, I mean a heat pump. So I can connect any thermal engine with a Carnot engine that acts as a heat pump. And what I get is that all engine that has the same efficiency as the Carnot engine, all engines that are reversible have the same engine, the same efficiency of the Carnot engine, because otherwise I could use the most efficient one in order to transfer more heat to the source, so the high temperature heat reservoir, and then violating again the statement of Kelvin or of Clausius. So essentially, all reversible engine acting on the same heat sources has the same efficiency of the Carnot engine. And so this is not only the efficiency of this Carnot engine, but of any reversible engine working on this temperature. Now, what I can do is to manipulate the comparison between the efficiency of a real engine and the efficiency of a Carnot engine, which is this one, in order to obtain that the sum on the cycle of the heat transferred divided by the temperature at which this transfer occurs, the sum of all of this is less than zero. This is the Clausius theorem, and since I can decompose any real cycle in a certain number of Carnot cycles, this is a general theorem, say that the integral over a cycle of the heat transferred divided by the temperature, clearly it has to be computed on reversible curves, is less than zero. And this for a reversible curve it is zero, because they are Carnot engine, and so it means that this the integral of q sub t is zero for reversible engine, and it implies that this is a state function, because one of the characteristics of state function is that the variation in a cycle is zero. So if I have a reversible cycle, I can define a quantity. So, okay, I can always define a quantity which is called entropy, whose differential is dq sub t, and has to be computed on reversible path, because it has to be a curve on the Clapeyron plane. If the whole engine is reversible, then this integral is zero. It means that you don't have any production of this entropy. Otherwise, this integral is less than zero. Now we can say, okay, let's suppose I have an irreversible transformation from A to B, and a reversible one over which I can compute entropy. I have to compute entropy only on this one, because by definition. Then I know if by reversing this reversible transformation, I have a cycle, and I know that this computation on the cycle is less than zero. It means that I can reverse this, so I have all of both transformations that goes from A to B, and so it means that this reversible is always larger than this computed on the irreversible one. Now, since this defines the variation of entropy, only those on the reversible defines the variation of entropy, I see that in case I have a closed system, so the Q from this side, the real transformation is 0, and then this is 0, and it means that in closed system, no, the variation of entropy is greater or equal to 0. Equal to 0 if the transformation is reversible, greater than 0 if the transformation is irreversible. So for instance, I have a closed system in which I have a gas confined, say, into a rubber balloon or in one side. I make the balloon explode, the gas distributes over all the system. Okay, the entropy has to increase because transformation is irreversible and the system is closed. I have two pieces of a body at different temperature. I put them in contact. The system can be considered closed. It does not exchange heat with other sources. Then the entropy has to increase. So essentially, this is the definition of entropy, which has again to be computed on reversible path, also for an irreversible transformation. Okay, in order to understand the basic idea of what entropy is, let us consider the working of water wheels. This is essentially an analysis done also by the father of Carnot and also by others. And the idea is that there are several different ways of moving a water wheel. For instance, by letting the water have a certain velocity and impact on the fences of the water wheel, or having it feel it at a certain point and then have it transimate when during the movement, or forcing it to stay inside the water wheel for all the time. Okay, this is the most efficient one because essentially I'm not wasting any potential or kinetic energy into what? Into turbulence, so essentially into heat, or just simply losing it because I have a finite jump in the height. So I marked here where dissipation is, and so essentially I can make a rather strict analogy between water wheels and thermal engine, where the equivalent of the temperature is the height, and the equivalent of heat is just the energy which is exchanged between a certain source of water and and the engine, or the engine and the other source. So you see that since heat it is nothing but energy, then the analogy is complete. And this means that I can also define an efficiency for thermal engine, which is just the amount of work done given a certain input energy on input. And for reversible engine, for reversible water wheel, I have a relationship which is very reminiscent of the Carnot one. And also for water wheels, I can make the same reasoning as for thermal engine. I mean, if I have a reversible, so I can use a water wheel also as a pump, just by turning it opposite side, I can use it to pump water up. And clearly, a reversible water wheel is a water wheel that, when is used as a pump, can pump up the same amount of water that was used to generate the work that I needed to perform this pumping. And I can demonstrate that all reversible water wheels have the same efficiency, otherwise I violate the conservation of energy. And so essentially I get a complete analogy between water wheels and thermal engine. Now we can use it to find the equivalent of the entropy. I mean, the entropy is just dq over T, which is, by analogy, the energy entering, so GHdm divided by temperature, which is H. So essentially it is GdM. And G is just a constant. I'm not interested. So essentially the equivalent of the entropy for a water wheel is the amount of mass of water which is entering or exiting the engine. And so clearly this is the reason why I have to discharge heat in a thermal engine, because in a water wheel I have to discharge water because I cannot accumulate water inside the water wheel. And for non-ideal water wheels, I discharge more energy of what is entering. Partial, so I discharge more the same amount of mass and some energy which is not has not been used. But now I can use the Einstein relationship mass energy, and so essentially I can see that I am discharging more mass of what has entered. And the same occurs for thermal engine. In thermal engine, normally I discharge the same amount of entropy that entered, but in non-reversible engine, I discharge more, so I convert energy into entropy, and so I discharge more entropy of what entered into the machine. Now, for finishing, we can, first of all, generalize the first principle, introducing also the possibility, for instance, of chemical transformation, so changing the number of particles. In order to do that, I have to define the chemical potential, which is the variation of the internal energy when I perform a transformation at constant energy, constant work, in which I add or I remove some of molecules. For instance, if a molecule is attracted by other molecule, I have to furnish work in order to extract it. So essentially, I lower, for instance, in evaporation, I lower the internal energy, and so this chemical potential is negative. Clearly, if these particles only repels each other, like in ideal gas, I remove a particle, then in this case I increase the energy or let it equal. And so this chemical potential can be either positive or negative or zero angles. And we shall see now in a moment what is the potential energy for an ideal gas. And by now writing in place of delta Q the equivalent from the entropy, so TdS in the work is this one, I have this formulation of the first combined with the second principle, which define a thermodynamic potential, which is the internal energy, expressed in terms of the variables S, V, and I. Now we shall reobtain this in a different way by starting, say, from a formal definition of thermodynamics. We start saying, okay, exists a quantity called entropy, which is an extensive function. I mean, it doubles if I double the system without that having interaction among these two pieces. So other extensive variables are volume and the number of particles, for instance. And the main point is that this entropy function, when the system is interacting, is a convex function. So the entropy of the system composed by two parts is equal or greater than the entropy composed by the entropy of the two separated parts. If they do not interact and they are the same temperature, etc., it is simply the sum. And also another point which is actually violated in some cases is that S is a monotonic growing function of energy, and so I can define a temperature which clearly agrees with the normal temperature, as the derivative of the entropy with respect to the internal function, which is 1 over t. We shall see in the following that actually sometimes, for instance, in lasers, I can have a system which is bounded in energy. So if I increase energy, entropy diminishes because the system becomes more ordered. And in this case, I can define negative temperatures, which are actually hotter than positive one. Okay. The equilibrium is the maximum of S. We have seen that the S always increases for, say, irreversible transformation, so I can assume that I let the system relax, that all irreversible transformation possible occur, and that at the end I have entropy which is at the maximum value, and this is essentially the equivalent of the second law of thermodynamics. Now, I can quickly verify that if I have a system composed by two systems that only interact through temperature, so they are separated by a diathermic wall, and so the energy is the sum of the energy, and also the other and all the other thermodynamic coordinates are constant. Then, by maximizing the energy with a small variation of one, the internal energy of one of these, I found that the two derivatives has to be the same, and this implies that the temperature of one is equal to, here I have a minus, is equal to the other temperature. So essentially, the equilibrium condition for systems that are in equilibrium through thermal exchange is that they have the same temperature, which is essentially the zero principle of thermodynamics. Now I can do the same using a movable diathermic wall, so I have to have the same pressure and the same temperature, but I can obtain this result by computing the maximum of the entropy with the partial derivatives with respect to energy and with respect to volume, and I found as before that they have the same temperature and the same pressure. So the pressure in this case is defined as P over T is the derivative of the entropy with respect to the volume. Finally, I can do the same by using a semi-permeable membrane and letting a particle pass from one side to the other, and I again find that I can define the chemical potential as the partial derivative minus mu over T is the partial derivative of the entropy with respect to the number of particles, variation of the number of particles, and again I found that if I have chemical and thermal equilibrium, then I have the same amount of temperature and of chemical potential. For instance, if I let only mechanical but not thermal equilibrium, I found that I cannot find a solution because I have too many variables essentially with respect to the conditions. So the system, for instance, if it is already in equilibrium, stays in equilibrium, but if it is out of equilibrium, the mobile while wall will continue to oscillate unless I assume some other mechanism. Okay, now in this axiomatic formulation of thermodynamics, the equation of state is just the expression of the entropy in terms of all extensive quantities. For instance, this is the Sackur-Tetrode equation that says how the entropy depends on all extensive variables, so the number of particles, the volume, and the internal energy. And from this, I can take the derivatives. I found that the variation of the temperature is given by this derivative, and this implies that I can use it to obtain U in terms of the temperature, which is one of the results that will come. So since the Sackur-Tetrode formula comes from statistical mechanics, this is also one of the results of statistical mechanics. The pressure is given by this, so essentially this is what is generally called the equation of state of an ideal gas, but actually all three of them are or this one are the equation of state of the the ideal gas, because for instance from here I can get that the specific heat is 3 over 2 kb, the specific heat for number of molecules, or if I convert it into moles, it's 3 over 2 r. R is just kb times the Avogadro number. And so this is, for instance, the potential, the chemical potential of a perfect gas, and one can check that this is positive because in an ideal gas, molecules essentially bounce each other, so they essentially repel. So if I remove a particle, they have more room, and essentially temperature lowers, and so the heat, the internal energy lowers, and so the chemical potential is positive. Up to now, we have worked defining the energy, the internal energy, as a potential, as the function, while the entropy, the volume, and the number of particles are the control variables. So one should modify a bit the entropy, modify a bit the volume, modify a bit the number of particles in order to have variation of the internal energy. This is not always simple. In particular, it is not always simple to make a transformation that keeps a constant one of these variables. And so it is convenient to change the potential. Before doing that, we have to establish the equivalent condition. For instance, for the entropy, we have seen that the equilibrium corresponds to the maximum of entropy. But since entropy is a convex function, this was one of the postulates, it is evident that we can cut this convex function with the surface as a constant entropy, and in this case the condition is that of the minimum of the free energy. So the equilibrium in the energy scheme is the minimum of the internal energy. Notice that the entropy, volume, and number of particles, as is also the internal energy, are extensive variables in the sense that if we double the system, then we double the entropy, we double the volume, we double the number of particles, and we double also the internal energy, and we shall exploit this condition in a minute. Okay, so we can change also the thermodynamic potential by doing a so-called Legendre transformation. And for instance, we can define the Helmholtz free energy, F, which is U minus Ts, and by taking the differential of all of these, also with respect to T and S, it can be seen that in this case the F depends on temperature, volume, and number of particles. And this is particularly convenient, this potential, when we shall deal in statistical mechanics with the system at a fixed temperature, a system that have a fixed volume, a fixed temperature, so that the free energy only depends, say, on the number of particles. And so it is also possible to define other kind of potential, for instance, the enthalpy, which is quite useful in chemistry, which is the internal energy plus PV, so that one exchanges essentially the control from the volume to the pressure. And this is particularly convenient because it is much easier to have a chemical reaction at fixed pressure instead of having a fixed volume. Suppose that the transformation generates heat tends to make things expand, and so you have to use a very, very strong vessel in order to keep the volume constant, while it is much easier to have a transformation at constant pressure. Clearly, here the entropy is a kind of control parameter, which is rather difficult to measure. But since TdS is dq, it essentially one measures the heat exchanged in the transformation, and if pressure is constant, one can see that one can get the heat exchanged by measuring the chemical potential and the number of particles. And it is possible to define other quantities, for instance, the Gibbs free energy. In this case, we exchange also temperature with entropy, and so we have now temperature, pressure, and the number of particles, or the Grand potential, which is the potential of the Grand canonic ensemble that we shall meet in 2 lessons, which is called sometimes Grand potential, and phi is U minus Ts minus the chemical potential times the number of particles, so that now I can also control the number of particles by modifying the chemical potential. And finally, notice that since we have seen that the internal energy is an extensive variable, as is the entropy, the volume, the number of particles. This means that if we multiply by some factor, for instance, double, the internal, the control parameters, also the internal energy should change by the same amount. So essentially, the internal energy is an homogeneous function of the variables. And if you take the derivative with respect to lambda and then put set lambda equal to 1, one obtains that u, taken here with the derivative with respect to lambda, is equal to s times du in the s plus v times du in the v plus n times du in the n. But since du in the s is the temperature, du in the v minus the pressure, and u in the n is the chemical potential, one gets that actually u is Ts minus Pv plus mu n. And so one can derive that the Helmholtz free energy is minus Pv plus mu n. The Gibbs free energy is simply mu times n, and the Grand potential is minus Pv, which will be useful for deriving quantities. Clearly, one could also try to, for instance, to eliminate also this, but you see that, for instance, if you take the Grand potential and you try to add also PV, you get simply 0. So you cannot have a thermodynamic potential with control parameters that are all intensive variables. You need at least one extensive variable. Okay, that's all for this lesson.